Vectors are undoubtedly the most important topic in physics. There's absolutely no way that you can do physics without knowing vectors. So you better pay attention. Let's begin with the chapter on vectors. So you're very welcome to today's lecture on vectors. I'm your personal physics tutor, Dr. Rima McMullen. So in this chapter, the first thing that we're going to discuss is what are vectors? And once we have figured out what vectors are, next thing we're going to look at is why do we need vectors? What is the need for using vectors? All right. And once we know what vectors are, why we need them, then we are going to look at how to represent them in physics. And after learning how to represent vectors, we're going to look at how many different kinds of vectors are there and how to perform mathematical operations on vector quantities. What kind of mathematical operations? Well, there is addition and there is subtraction, but not just that. There is multiplication, and you will be glad to know that you do not have to learn how to divide vector quantities. Why? Because we simply do not divide vector quantities. We're going to learn that vector multiplication, it is of two kinds. Vector multiplication is not simple like scalar multiplication, where 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and so forth. When we talk about vector multiplication, it is very specific kind of multiplication. It's of two kinds, dot product and cross product. All right. So moving on, in this lecture, we are going to go over what are vector quantities, why do we need vectors, how do we represent vectors, and what kind of vector quantities are there. This will become a very long lecture if we try to include mathematical operations such as addition, subtraction, and multiplication. And the rumor is that the students these days do not have a very long attention span. So I'm not about to make a super long lecture, although I do have some super long lectures. But this one, I'm going to try to keep it short and simple and work on only what are vector quantities, why we need vector quantities, how do we represent them, and how many different kinds of vectors are there. So are you ready for it? Well, I am. Let's jump into it. So what are vectors? Vectors are physical quantities that have both magnitude and direction. In contrast to scalar quantities, scalars are physical quantities that have only magnitude. While vectors, they are physical quantities that have both magnitude and direction. Quite simple, I hope. All right. So we said that there are two kinds of quantities, vectors and scalars. They both have magnitude, while only vectors have direction. Now here's a question for you guys. What does magnitude mean? Magnitude means how much. So for example, if we say that 2 cups of coffee, where each cup has 8 ounces of coffee. So here the magnitude of coffee is 16 ounces in all. So this number, the number that is telling you how much of something is there, that is called as its magnitude. Alrighty. Well, so we have been talking about that vectors and scalars, they are physical quantities. So let's make sure that we understand what's a physical quantity. A physical quantity is something that can be measured. Anything that you can measure is a physical quantity. Can you measure the mass of an object? Sure can. That's a physical quantity. Can you measure the temperature? Sure can. That's a physical quantity. Can you measure the volume of liquid? Yes, we can. That's a physical quantity. Can you measure the pressure in a tire? Yes, you can. That's a physical quantity. Can you measure the speed of a car? Yes, you can. That is a physical quantity. Can you measure the brightness of a bulb? Yes, you can. That is a physical quantity. Can you measure the force applied on an object when you push on it or you pull it? Yes, you can. That's a physical quantity. So there are different kinds of physical quantities. All the things that can be measured using any kind of tool or device is a physical quantity. And in general, physical quantities are of two kinds, scalar and vector. So this chapter, it is devoted to vector quantities. All right. So hopefully now we all know what's a physical quantity. That is something that can be measured. How many kinds of physical quantities are there in general? Scalars and vectors. Scalars are physical quantities with only magnitude, while vectors are physical quantities with both magnitude and direction. All right, moving on. Already said that there are two kinds of physical quantities, scalars and vectors. And scalars have magnitude only, for example, mass and temperature and speed. So temperature and speed, that is kind of hiding behind my image over there. I guess I could make my image a bit smaller, but if on the subsequent slides it seems like my image is too big, then I'll reduce it in size. Moving on to the examples of vector quantities. Velocity, pressure, force. All right, what else? Momentum. Now you may or may not have heard of these things, although I have a feeling that you have already heard about force, momentum, pressure, and velocity. These are very common physical terms. Alrighty. So far we have discussed what are vector quantities. Now the natural question to ask is, why do we need them? Why can't we just do without vector quantities? Well, let's see. So here on this slide, we have this little kiddo. What do we call him? Let's call him Tom. Why not? Tom wants to go from his home to the park. So the park is 250 meters from Tom's home. But how does he get there? To go there, first he goes 100 meters east. Then he goes 100 meters up north. Then he turns east and goes another 50 meters to reach the park. So to go from his home to the park, we have to tell him not only the distance, how much distance he needs to travel, but we also have to tell him in what direction he has to travel that distance. So these numbers here, 100 meters, and 50 meters, these are called as displacements. These have direction, east, north, east. They have magnitude and direction associated with them. So therefore, these are vector quantities. So many times when you talk about a physical quantity, it is not sufficient to give just a number. You also have to tell a direction. For instance, let's insert another slide here. Let's say there's a box sitting on the ground and you want to bring it home. This is the door. So let's say there's this box sitting outside the door and you want to bring it in your home. So let's say a box has been delivered to your home. You want to bring it in. You want to push it along the ground through the door into your home. Which way are you going to push it? Of course, this way. You have to exert a force toward your home. You could either push it or you could pull it, whatever you do. It's important that you exert that force toward the door, not away from it. Because if you exert the force away from the door, then you're doing opposite of what you need to do. Therefore, for quantities such as force, pressure, momentum, velocity, displacement, and many more, there's not only a magnitude needed to describe it, but you also need a direction. Because in the absence of the direction, you won't learn much from the number, from the magnitude alone. I hope that makes sense. All right, moving on. Now that we know what are vectors and why we need them. Vectors are quantities that have both magnitude and direction. And the reason we need them, because in nature, all around us, there are quantities where to completely describe them, we need to associate not only a magnitude, not only a number with them, but we also need to assign a direction. Without that, the information is incomplete. Make sense? Sure hope so. The next thing we're going to do is look at how we represent these vectors. Now these vectors, they are represented by arrows. So the arrow's length, it tells you the magnitude, while the direction of the arrow tells you the direction of the vector. So here in this case, D2 is displacement. 2, the subscript, well, we write these subscripts like D1, D2, etc., to distinguish between different quantities. So all of these D's here, all the D's mean displacements. But the displacement could be one going this way, the other going this way, the third one going this way. How do we differentiate between them? By putting this subscript. How do we know that we're talking about displacement, which is a vector, and not the distance, which is a scalar quantity? For that, you will put this arrowhead over the quantity. This arrowhead over the symbol, it tells you that we are talking about a vector quantity. And in some books, you will see that in place of putting this arrow over the symbol, they will use bold letter. So bold letters, they can also be used to represent a vector quantity. That means a scalar will be represented by, what's the opposite of bold letter? Whatever letter is not bold letter, unbold letter. Unbold letter will be used to represent scalars, and bold letter will be used to represent vectors. Otherwise, if I have this one D and this other D, then I would guess the first one is distance, if I'm not told anything else. The second one is displacement. It got cut off. Here you go. Cool? Cool. Move on? Yes. Looks like I have to scale my videos down. Let me make it smaller. Alright, here we go. Now we have two vector quantities. The arrow representing D1. It is half the length of the arrow representing D2. Why? Because D1's magnitude is 5 meters, which is 1/2 the magnitude of D2, which is 10 meters. So far everything is fairly straightforward and easy. I'm sure you're all getting it. Moving on. Representation. Aha. Now we're going to talk about Cartesian coordinate that I'm sure that you're all familiar with. Let me do one thing here. Let me fix it. I'm sure you're all familiar with Cartesian coordinates, our old friend X, Y, and Z coordinate system. It is called as Cartesian coordinate system. Alright. So in Cartesian coordinates, we know that there are 3 axes, X, Y, and Z. And these 3 axes, they are related to each other by right-hand rule. So here, could it be that this was minus and this one was positive Z? No. Why not? Because, let me erase it, because this is wrong. It couldn't be like this. And the reason is this. X, Y, and Z axes, they are related to each other by right-hand rule. Some people like to use 3 fingers like this of the right hand. Pay attention to the word right hand, especially if you're lefty. If you use your left hand, you're going to get wrong direction. So in place of using these 3 fingers the way they are shown here, I like to use a different version of right hand rule. What I do is, well, by the way, this right hand rule, it tells how X, Y, and Z coordinates, they are related to each other. And what does right hand rule say? It says that point your right hand fingers in the direction of x-axis. And I see now that since I am sitting across from the screen, my left and your left, they are swapped. So let me do one thing. Let me swap my image. But even with that, there's going to be a little bit of an issue, but we'll deal with that. All right. So now my right hand fingers, they are going along the x-axis, positive x-axis, which is going to the right. Now my fingers, they could face you, they could face down, they could face backwards, I mean like this maybe, but they have to point along the x-axis. So once I have established the direction of the x-axis, then I have to curl my fingers toward y-axis. So that means my fingers have to go up. So my right hand fingers, first I point them toward x-axis, then I curl them toward positive y-axis. So positive x-axis, positive y-axis. Which way does your thumb go? It's going to go out of the screen. So to you, it's going to seem like my thumb is going into the screen, but it isn't. Why? Because I'm sitting right across from the screen where I'm recording it. And as per the screen where I'm recording it, it's coming out of the screen. It's going toward my nose. So here you go. This is the way thumb will go. And the direction of the thumb will be the direction of the positive z-axis. Likewise, I could have pointed my right hand fingers toward positive y-axis, which is upward, and then curl them toward the positive z-axis, which is coming out of the screen. So here, to you, it's going to look like my fingers are going into the screen, but for me, they are coming out of the screen. If you don't believe me, get your own right hand out and try it for yourself. And now your thumb, it's going to go to the right in the direction of the positive x-axis. Just the same way. Point your right hand fingers coming out of the screen, that is in the direction of the positive z-axis, and then curl them toward right, going in the direction of positive x-axis. Thumb goes up. That's the direction of the positive y-axis. Hopefully it's a review for you. Hopefully you already know that xy Cartesian plane, it can be divided into 4 quadrants. It can be divided into 4 quarters. The first quarter, it's going to go from 0 degree. Where's the 0 degree? This is along the positive x-axis. This is 0 degrees. Okay. From 0 degrees to you go counterclockwise. Positive y-axis, it is 90 degrees. This is your first quarter. Okay. Moving on. Second quarter, that is between this is here 90 degrees. This is here along the negative x-axis. All right. Third quadrant, it goes from negative x-axis, which is 180 degrees, to negative y-axis, which is 270 degrees. Then we have the fourth quadrant, which goes from negative y-axis to positive x-axis. Along the negative x-axis, we have 270 degrees and positive x-axis is 360 degrees. A cycle has been completed. A cycle has 0 to 360 degrees. Just like a circle has 360 degrees internal angle. You all knew that? You better. All right. So now the next thing we're going to do is see how to represent vectors on this Cartesian plane. So we're going to see only 2-dimensional vectors here. Moving on to the next slide, we have 2 vectors, vector A and vector B. Okay. Now you tell me, vector A, what quadrant is it in? Which quarter it is in? Same as vector B. Which quarter is it in? Is vector A in quarter 1, 2, 3, 4, or if you want, you can call it as quadrant. Is that in quadrant 1, 2, 3, or 4? The arrow has a tail. The vector begins at the tail. It ends at the arrowhead. So what we want to do is begin the arrow at the origin of the coordinate frame. So we're going to take this vector and move it parallel to itself, that is without changing its direction, and move the tail of this arrow to the origin of the Cartesian coordinates, like this here. So here you go. What quadrant is it in? second quadrant. Just by looking at the direction of the arrowhead, you could tell. So that's vector A. Let's move it over. All right. Now, which quadrant do you think vector B is in? How would you figure it out? You're right. You're going to move vector B parallel to itself until its tail coincides with the origin. All right. So here you go. You moved it. What quadrant is it in? Sure, it's in quadrant 1. There you go. This is how you represent vectors in the XY coordinate plane. Um, in the next lecture, we are going to learn how to split these vectors into components along x-axis and y-axis. In this lecture, I wanted to keep it more qualitative. I don't want to get into how to resolve it into components, what kind of angle we are talking about, and all that stuff. We'll do that very soon in the next lecture. And hopefully by the time this lecture will be published, the other one will be ready. Alrighty. So now that we know what are vectors, why do we need vectors? How do we represent vectors? We are ready to move on to different kinds of vectors. Vectors are physical quantities that have both magnitude and direction. We need vector quantities in physics because not all quantities can be described completely using just a number. Many of them, such as force, pressure, momentum, displacement, velocity, acceleration, they require both magnitude and direction to completely describe them. Now, how do we represent vectors? We represent vectors by using a symbol like this over here, A and B, and put an arrow over the symbol. This arrow over the symbol, it means that it's a vector quantity. In addition to that, we could use an arrow literally, and the length of that arrow is going to tell us the magnitude of the vector, and the direction of the arrow is going to tell us what? The direction of the vector. All right. Now, how many different kinds of vectors are there? Many actually. A zero vector, called as a null vector. Unit vector, perpendicular vector, equal vector, negative vector, parallel vector, and antiparallel vector, collinear vector, coplanar vector, co-initial vector, normal vector, orthonormal vectors. What we are going to do now is go over each of these one by one. It's actually very simple. It's just terminology. It's just nomenclature. Nothing more than that. So zero vector or null vector. Null in mathematics means zero, means absence of anything. Absence of anything is null or nil. We call it as null vector, just like null set in set theory. Why do we need zero vector? Well, if you take some vector A and subtract another vector, call it A. A minus A, what does it give you? It gives you a third vector, a zero vector. This is a zero, but it's a vector quantity. So when you subtract a vector from itself, you get something. Whatever you get, that vector is a zero vector. Therefore, we do need to have zero vectors. So zero vector can be added to a vector, or it can be subtracted from a vector, and the resultant will be the vector itself, whatever the non-zero vector is. And in addition to that, if a vector is subtracted from itself, whatever results is a zero vector. Easy. A zero vector will have how much magnitude? Zero. What will be the length of the arrow representing it? Zero. Easy? Yes. Moving on. Unit vectors. Now, unit vector here, unit has a very specific meaning. Unit vector means a vector that has magnitude equal to 1. That's where a unit means here. The only significance of unit vector is to specify direction. Okay, so it has magnitude of 1 and it is used to specify direction. In Cartesian coordinates, we said we have 3 directions. X-axis, we have y-axis, and we have z-axis. So the unit vector that goes along x-axis, it is called I hat. So we put a hat, a cap over the vector. That cap or the hat represents that it is a unit vector. So I hat, it's a unit vector along the x-axis. J hat, it is a unit vector along the y-axis. K hat, it's a unit vector along the z-axis. Now think about the English alphabet. A, B, C, D, E, F, G, H, I, J, K, I, J, K, I, J, K. They come in order, just like X, Y, Z, X, Y, Z. They come in order. I, J, K. They come in order. So it's easy to remember. X, Y, Z, the last three letters of the alphabet, and I, J, K, somewhere in between. Well, not exactly in between. Somewhere there, but in order. I is to X, J is to Y, K is to Z. And these are unit vectors. They represent direction only. What is their use? You're going to see their use in the next lecture when we learn how to split a vector into components. Okay? All right. Moving on. Perpendicular or orthogonal vectors. The name tells you. Perpendicular vectors, when two vectors call A and B. These are perpendicular to each other, means at right angle, at 90 degrees to each other. Such vectors are also called as orthogonal vectors. Orthogonal is a synonym for perpendicular. So just on the last slide, we looked at unit vectors I hat, J hat, K hat. Those vectors are mutually perpendicular to each other. They are orthogonal vectors, right? Right. Okay, so now we know what are zero vectors, unit vectors, perpendicular or orthogonal vectors. Moving on. Equal vectors, equal magnitude and pointing in the same direction. If you have two vectors, they are absolutely equal in length, in magnitude, and in direction. They're equal vectors. How do you represent them? Well, vector A equals vector B. They're both going to be exactly identical. Absolutely no difference. No difference, no way you can tell A and B apart. That's what equal means. Okay, here you go. Here's an example. We have two vectors, A and B. They're both 10 meters in length and at 45 degrees. So they don't have to be right on top of each other. They could be wherever in the space. One could be here, the other could be on Mars if you want. But as long as they're oriented in the same direction and have same magnitude, they're same vectors. Well, it will be interesting if one is on Earth and the other is on Mars, because well, I'm getting into technicalities here. Earth and Mars, they're both spinning on their own axis, then they're spinning, then they're revolving around the sun, and then the whole solar system is spinning, galaxy is spinning. So in all these spin rates, they're going to be different based on where each of these objects are. So I don't know how to keep two vectors equal to each other, but who cares? We're talking theory here. So in theory, you could have one vector on Earth, other on the Jupiter if you like, as long as they're both in the same direction and have the same magnitude. For all we care, they are equal vectors. All right. Negative vectors. Negative vectors are, so equal magnitude, opposite direction. A and B as shown here. Once again, you could put one on Saturn and the other on Venus if you like. And as long as they are going in the opposite direction, here like my arms here that are not fitting on the screen. I can't. Here you go. Two vectors. See their arrowheads? See them? See them? So here you go. Alrighty, what is next? Parallel vectors. I bet you can never guess what are parallel vectors. Parallel vectors are, as the name tells, they are parallel to each other. They can be of same or different magnitudes. They can be in the same direction, that is parallel, or they could be anti-parallel. That's also sometimes called as just parallel. So equal vectors and negative vectors, they are a subset, they are a subclass of parallel vectors. So equal vectors are kind of parallel vectors, and negative vectors, they're kind of anti-parallel vectors. Equal and negative vectors, they are equal in magnitude. However, parallel and anti-parallel vectors, they have to do only with the direction, not with the magnitude. Cool? Cool. Moving on. Collinear vectors. Collinear vectors and parallel vectors, they are basically the same thing. Parallel vectors and collinear vectors, they are the same things. They both mean vectors are parallel to each other and along the same line. Now the same line, it doesn't have to be exactly the same line. Lines can be shifted, okay? But they have to be parallel. I know it's kind of confusing. You would think that, if I had to guess it, I would say parallel means literally parallel but shifted anywhere in space, while collinear would mean something like this along the same line. But that's not what it actually is. Collinear actually means parallel. So here you go. Parallel and collinear, they are the same things. Coplanar vectors. Duh, in the same plane, just like all the vectors I'm drawing here. I'm drawing them on the same computer screen. So these are all coplanar. None of these is equal or parallel or anti-parallel or negative or perpendicular or zero. But they're all in the plane of the screen. So they're all coplanar vectors. Co-initial vectors. There you go. All vectors lie in one plane. They may have different magnitudes and directions. Got it. Moving on, co-initial vectors. Co-initial. Initial means starting. They start at the same point. Okay, co-initial, something like this. Here's one vector. Let's begin another word at the same place. These are all co-initial vectors. They are beginning at the same point. On a coordinate frame, x, y, when all of the vectors on that plane, they're all beginning at the origin, they will be co-initial vectors. Normal vectors. Normal vectors actually is a synonym for perpendicular vectors. Normal vector. It makes 90 degrees angles with the line or the surface. So basically, it is perpendicular. That's all it means. In mathematics, there are different terms that are used to mean 90 degrees. Perpendicular, right angle, orthogonal, normal. They all mean the same thing. I have put them all here actually, except for right angle. Right angle, perpendicular, orthogonal, normal. All mean the same thing. Last, orthonormal. So what I'm about to say now might sound like I'm contradicting myself, but I'm not. This is how. Orthonormal. It's a combination of two words. Ortho, it is one, and then we have normal, second. And I just said over here that normal and perpendicular are basically kind of same things, right? 90 degrees. But over here, ortho means this orthogonal, 90 degrees. But normal does not mean this normal over here. This normal here means the vector is normalized. And what does it mean to normalize a vector? When you divide a vector by its own magnitude, okay? So let's say you have vector A. You divide it by its own magnitude. This is how you represent magnitude. What you get is a unit vector that's going to be in the direction of this vector A. So all such vectors that are perpendicular to each other and they have unit magnitude, they are called as orthonormal vectors. So I hat, j hat, and k hat. Those three vectors are orthonormal. I know this is probably, beyond what you need to get into here, but for some of you, you might be very, very interested in physics. You might love physics so much that I want to give this to you. I do not want to deprive you of, what you could be learning here. Here we go. Unit vectors that are mutually perpendicular. So here you go. Congratulations. You have made it this far, and so have I. So in this lecture, we have looked at the basic foundation of vectors. We have learned what are vectors, why do we need them, how do we represent them, and what kind of vectors are out there. In the next lecture, we're going to look at how to represent vectors in the Cartesian plane, how to resolve vectors into components. And in the lectures following that, we're going to learn at how to add and subtract vectors using different methods. And lastly, we're going to learn vector multiplication, dot product and cross product. And along with all those lectures, we're going to make lectures on problems, because you know physics only when you can solve problems. And we are going to solve a whole bunch of them on this channel over here. So here on this channel, we're going to do all of Physics 1. I'm going to do it algebra based as well as calculus based. I hope that this lecture was useful to you and that you learned from it. If you appreciate my humble effort of passing on the passion and the love for physics, math, and education in general to the next generation, then please do like this video and subscribe to the channel. It means a lot to me. And if you have any questions regarding what we are learning, please put them in the comment section and I'll do my best to get to it. All right. Well, thank you for watching. I'll see you again very soon next time. Until then, have a good one. Home means same.